The next example I want to look at is some trig functions. So let's go ahead and look at the limit as x approaches pi, that's very exciting, of sine squared of x over 1 plus cosine of x. Always put parentheses around the arguments of your trig functions. First thing we always do with the limit is we just go ahead and plug in our limiting value. So we go ahead and plug in pi and see what we get back out. If we have a reasonable answer, I'm done. However, if I have a 0 in the denominator, or 0 over 0, or I'm about to learn about infinity over infinity, I know I have a problem and I'm going to have to work a little bit harder at this. 1 plus cosine of pi. Okay, in the numerator, the sine of pi. Well, if we look at a quick look at our unit circle, here's pi over in this direction. The sine, of course, is 0. 0 squared is 0. The cosine of pi is negative 1. 1 plus a negative 1 is 0. I get 0 over 0, which is indeterminate. And I know now it's not only indeterminate, it's indeterminate L'Hopital's. So let's go ahead and apply L'Hopital's rule. Now remember, if L'Hopital's rule is going to work, this next set of limits that I take have to exist. Derivative of sine squared of x is where I want to start. So the derivative with respect to x of sine squared of x. I'm going to rewrite this as sine of x quantity squared over the derivative of the denominator, and our denominator is 1 plus cosine of x. Okay, so let's go ahead and actually take those derivatives. When we take the derivative of sine of x quantity squared, it's the chain rule. You bring the 2 down, decrease the exponent by 1, multiply it by the derivative within. The derivative of the sine of x is the cosine of x times the derivative of x. The derivative of 1 plus cosine of x is easy because the derivative of 1, the derivative of a constant is 0, and the derivative of cosine of x is a negative sine of x. We can get some canceling to occur here. The sine of x's cancel, and I am left with the limit as x approaches pi of negative 2 cosine of x. The negative, of course, is flipping up from the denominator. Now let's go ahead and plug our pi back in. Cosine of pi is negative 1. Negative 2 times negative 1 is a positive 2. And so 2 is my limiting value here. We can also check this out graphically, and we'll look at a graph in a second. And we can also look at this algebraically. So let's go ahead and look at the same limit algebraically. Limit as x approaches pi, sine squared of x over 1 plus cosine of x. In order to solve this one, we're going to use a trigonometric identity. When we plug pi in, we get 0 over 0, which is indeterminate. It's indeterminate L'Hopital's, but we're not going to use L'Hopital's rule, so I'll kind of skip that step. Let's look at the limit as x approaches pi. Now remember, this indeterminate means I need to do more work. And the more work that I know how to do is graphical, producing a graph in Maple or an algebraic approach. First of all, 1 plus sine squared is cosine squared, so I know that sine squared is equal to 1 minus cosine squared of x. And this is over 1 plus cosine of x. Now I've not done L'Hopital's rule, and I'm not going to do L'Hopital's rule. I'm just rewriting this, so hopefully something will cancel algebraically. 1 minus cosine squared is actually the difference of perfect squares. This is 1 minus cosine, 1 plus cosine, divided through by 1 plus cosine of x. And of course here we can see that the 1 plus cosines of x cancel, and I'm left with the limit as x approaches pi of 1 minus the cosine of x. Plugging pi directly in, this will look familiar, we get 1 minus a negative 1, which is 2. So I can verify this through L'Hopital's like we did up above, or I can use my algebraic approach. And next I'm going to pop in a very small graph right here in the corner so we can get a good look at what this graph is actually doing from Maple. So from our graph we can see the limit as x approaches pi. Here's pi right down here. So I'm approaching this y value, which is 2, so this verifies. Let's go ahead and look at another example next. And this next example, we are going to be getting a solution that I cannot use L'Hopital's with. So for this next example, let's take the limit. Let's see, get the pen working here. The limit as x approaches infinity of x e to the x. Well, we cannot plug infinity directly in. You know, we can't, there's no calculator that I can just plug infinity in and add and subtract infinity. But I can look at the behavior of a function as x approaches infinity. So if I think about the function x, this is just a line that goes through the first and the third quadrants. And as x goes toward infinity, this is an increasing function, so this goes to infinity as well. Now e to the infinity is just another degree of infinity. And of course, so we have infinity times infinity, which is equal to infinity. Therefore, the limit does not exist. Okay, let's go ahead and look at our next problem. And the thing to note here, I guess, is that this is not an indeterminate form. We didn't have to get to an indeterminate form to do anything. So we still have all the same ways of finding limits that we did before. But now if we come across that indeterminate form case, we kind of have to keep our eye out for it. Okay, the next example we're going to look at is the limit as x approaches infinity of x squared plus 4x plus 2 over 2 minus 9x squared. Now, of course, when we plug infinity in, and again, we can't really plug infinity in, we need to look at what's happening here. We have infinity squared plus 4 times infinity plus 2 is just going to be a very, very large number approaching infinity. In the denominator, I have 2 minus infinity, which is negative infinity. So here, this is an indeterminate form, and specifically, it's indeterminate L'Hopital's. So let's go ahead and apply L'Hopital's rule. Now remember, for L'Hopital's rule to work, this next limit must exist. And you can take very many iterations of L'Hopital's rule as long as the limits keep going to an indeterminate form step after step. The derivative of x squared plus 4x plus 2 is 2x plus 4. The derivative of 2 minus 9x squared is negative 18x. If I take my limit as x approaches infinity again, I get infinity over negative infinity, which is indeterminate L'Hopital's as well. So I do another iteration of L'Hopital's rule. Limit as x approaches infinity of the derivative of 2x plus 4, which is 2, the derivative of negative 18x, which is negative 18, and I get a negative 1/9 here for a solution. So my solution is negative 1/9. Let's go ahead and pop in a graph from Maple to see what Maple says. Okay, the graph from Maple is kind of almost a little bit confusing, because here, remember, I'm taking the limit as x approaches infinity, so I'm looking at this part of the graph, so I'm going out in this direction, and it looks like the limit as x approaches infinity is going towards 0 right here, but it actually is not. It looks like it's going towards 0, but we can see from our work that we've done over here that this limit is actually negative 1/9. So this graph is a little bit misleading. It almost looks like the limit is going towards 0, but it's actually going toward negative 1/9. And if you actually plug in the limit and the function into Maple, instead of just looking at the graph, you get negative 1/9 as well. Now there's other indeterminate forms that we have not talked about. Now of these other indeterminate forms, remember, only some of them are indeterminate L'Hopital's. So let's go ahead and look at the indeterminate L'Hopital's again. So indeterminate L'Hopital's was 0 over 0, infinity over infinity, and of course negative infinity over negative infinity, or positive infinity over negative infinity, etc. So these are our indeterminate L'Hopital's. Other indeterminate forms include one over 0 minus 1 over 0, 0 to the 0, 1 to the infinity, infinity to the 0, and infinity minus infinity, and 0 times infinity. These are all indeterminate forms. And you might say, well, wait a minute, 0 times anything is 0, so how could this be indeterminate? But I'm not talking about just arithmetic here. I'm talking about the concept of a limit. I'm talking about the behavior of a graph. So these are not, multiplying arithmetically. These are looking at the behavior of a graph at a particular point. Now these three right in the middle are indeterminate, but I have a specific way that I can work with these and solve these. For these, I will use the log function like we did with logarithmic differentiation, so I'll use that log function. So here I'll use ln to find the limit. Now each of these other ones probably has a little bit different approach that we're going to take. A lot of times with the 1 over 0 minus 1 over 0, we'll rewrite as a single fraction.